Now, this is Chemistry 3053, Organic Chemistry, Chapter 11, which it covers synthesis. This is going to give you some ideas about how to create a target molecule. So how do you get started? What considerations do you have to make, etc. And it will give you a few examples of putting together reactions that you've already had in order to synthesize a target molecule. So let's look at this. So first, a one-step synthesis, functional group transformations, reactions that change the carbon skeleton, how to approach a synthesis problem. And so, and then in the second, we're only going to have 2 videos for this chapter. It's a very short chapter. Retrosynthetic analysis, green chemistry, and practical tips for increasing proficiency. And there will be some review sheets in this last section. So let's go ahead and get started. A one-step synthesis, solving a synthesis problem. In other words, you have a target molecule. And very often you'll be provided what starting materials you need to start with, or you'll be told starting with any 2-carbon molecules and reagents that you want. And so here you're given the starting materials and the target molecule. Target molecule is often abbreviated TM. And so here you know that you would simply add Br2, and the Br2 would add across the double bond. No stereochemistry is specified. And so in these cases, you need to know what the reactions are, what the reagents are, and you need to know what all organic molecules that you might be able to select as starting materials also. In these situations, you'll be given the target molecule in each case. So this is one particular type of a synthesis problem where you're given the target molecule, and that's what you need to create. So functional group transformations. Here, let's say that you have a 2-step synthesis strategies that we're going to review from previous chapters. Here you need to move a functional group from C2, or rather, sorry, this is C3 to C2. 1, 2, 3, 4. So you simply need to move the functional group over by 1 carbon. So you start out with it being at the less substituted carbon. You want to move it to the more substituted carbon. And so you need to do an elimination that will give you a double bond across here, because then you know that you can do an addition to put the bromine over here. So this would be a Markovnikov addition, which you know you can do. And then you need to do the elimination to put the elimination only giving you the more substituted carbon-carbon double bond. That's going to be a Zaitsev elimination. And so let's see what that's going to be. So you know that using the smaller base is going to give you the more highly substituted alkene. If you used the more sterically hindered base, it would pluck off a proton only at the terminal carbon. So if you use the smaller base, you'll be able to pluck the proton off of the more highly substituted carbon, and then you will be able to get the more stable and more highly substituted triple bond. And then you will simply add HBr, your Markovnikov addition, and you will get the target molecule. This shows an alternative route if you had been trying to synthesize the molecule that had the bromine on the terminal carbon. That's moving bromine by 1 carbon, but it's moving it to the terminal carbon, the less substituted carbon, rather than the more substituted internal carbon. So this is a nice review. Now, that is for moving a functional group over by 1 carbon If it is bromine, if the functional group is bromine, this is the same problem, except here the functional group is an alcohol. The goal is to move the alcohol over one position and to give you the more highly substituted alcohol. And you have your alternative synthesis down here to give you the less highly substituted alcohol. And notice once again, the bases don't really change. Here you've got the less sterically hindered base to give you the internal alkene. Here you've got the more sterically hindered base to give you the terminal alkene. And then instead of adding HBr across the double bond, you simply add the hydronium ion, some acid with water. And notice, though, that in order to get the leaving group, alcohols are not a good leaving group. An alcohol is not a good leaving group. You started out with bromine before, and that's a good leaving group. So here you have an additional step at the beginning, and you need to convert this alcohol functionality into a good leaving group. And so what you do is you use tosyl chloride and pyridine. This replaces the hydrogen with tosylate. So this will be OTS, and that is a great leaving group, the tosylate. So the hydrogen is replaced, not OH, simply hydrogen is replaced. So the OH bond is broken, not the carbon-oxygen bond is broken, to convert this into tosylate. And so this is a very similar approach to what you saw previously. Notice that you can go back, and here you can go back very regiospecifically, and so you'll need to know these oxidizing agents as well, which will put the alcohol functionality at the less sterically hindered end, less substituted end, or you can put the alcohol functionality, here you're putting the alcohol functionality at the more sterically hindered and the more highly substituted end of the double bond. So here you have some complementary reactions and ways to control the regiochemistry. You can also do functional group transformations. Here we've moved the carbon-carbon double bond from being an internal to the ring to being external to the ring. How are you going to do that? Well, first you need to add HBr across the carbon-carbon double bond, and you need to do that with in a manner such that you'll put the bromine at the more highly substituted end of the carbon-carbon double bond. So that's going to be a Markovnikov addition, which you've had many times. And now you want to create the less substituted double bond, and so you're going to need a very sterically hindered strong base. So let's look at what this is. So here you're going to have a Markovnikov addition, and then you're going to use a very sterically hindered strong base so that you will pluck a proton off of here, and this base is too large to be able to go in here and give you back the internal carbon-carbon double bond. If you wanted to go the other way, in the other direction, here are the reagents that you would use. You would get anti-Markovnikov addition, and then you would use a very sterically hindered base to give you the double bond in moved over one position in the other direction. And so you see that you have these reagents which complement each other greatly. So let's see, you can also convert an alkane to an alkene, because you can brominate at this tertiary carbon by using radical bromination and then use elimination. You can make the elimination internal by using a very sterically hindered strong base, or you can make it terminal. Sorry, you can make it external by using a very sterically hindered base, or you can make it internal by using a base that is not very sterically hindered. So you have a lot of different choices that you can use in your reagents to be able to control the regioselectivity of these, where the functional groups wind up. You can also remember, this is review, convert a triple bond to a double bond, and then convert the double bond to a single bond, and you can go back the other direction. So you'll need to review all of these. You had a lot of different reactions. There'll be a very nice review sheet at the end of chapters 11, 12, and 13. And I urge you to use those. Changing the carbon skeleton. It's very easy to look at the molecule, at the reactants and products, and see if the carbon skeleton has changed, if you've gained carbons or lost carbons, or if the carbons are connected in a different way. This is very easy to see, and that's something that you need to do right at the very beginning. And if you do need to alter, you've had only a very small number of reactions that alter the carbon skeleton. Most of the reactions that you've had so far only change the functional group or change the location of the functional group. So you've had one reaction so far that enhances the carbon skeleton. So here you've got an alkyl halide, and here you've got an alkyne. You have removed the terminal proton here, the alkynyl proton, by using sodium amide, and now you've got a strong nucleophile. This is going to react here in an SN2 reaction, and so you have created this carbon-carbon bond. So you have changed. You start with a molecule that has 4 carbon atoms, and you've embellished it now so that you have 7 carbon atoms. And you could change this very easily by simply altering the alkyl halide that you start with. So you'll need to remember that. That's your one reaction that you've had that increases the number of carbons in your carbon skeleton. You've also learned a way to decrease the number of carbons in a molecule. If you have a carbon-carbon double bond, you can use ozonolysis and convert your 5 carbon atom alkene to a 4 carbon atom carbonyl. And carbonyls are very easily modified. Now, so how do you approach the synthesis problem? So you look to see if there's a change in the carbon skeleton. Is it gaining or losing carbons? Is there a change in the identity or the location of the functional group? Up here, you could also, it doesn't have to be gaining or losing carbons. There could be a change in the branching that you need to look for. So you need to look for both of these things initially if you're trying to synthesize a target molecule. And you'll need to be able to remember all of the reactions that you've learned along with their reagents. So propose an efficient synthesis for the following transformation. Notice you're starting out 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. And so you're going from a 5 carbon alkyne to a 7 carbon alkene. And notice you have put this 2 carbon unit here at the end of the unsaturated linkage. And so between 4 and 5, you start out with a triple bond, you wind up with a double bond in between 4 and 5. Now notice the numbering here. 1, 2, 3, 4, 5. This has nothing to do with nomenclature. You're just numbering it just to keep track of the positions of the functional group. This is not a nomenclature problem. So don't get confused and start thinking that this always has to be carbon 1. You can renumber these things depending on what your goal is. And right now your goal is to just keep track of where the functional groups are. And so the functional group, the unsaturated linkage, has not moved. And so how do you put an alkyl group at the end of your alkyne? Well, you just saw a way. You remove this proton with a strong base like sodium amide, and then you react it with an alkyl halide. And that alkyl halide is going to have 2 carbons in it. So, and then the triple bond will need to be converted to a trans-alkene. So let's look at this here. So you're going to use sodium amide to remove the proton at the end of the triple bond. Then you're going to react the alkynyl anion with ethyl iodide, and you will do an SN2 reaction here, and that will put the ethyl, the 2-carbon unit here, attached to the triple bond. And then you need to reduce your triple bond in a manner such that you get only the trans-alkene, and that's going to be with dissolving metal reduction, which you have already had. So here is the way that you would write this reaction. Now, I want to draw attention to something over here. Notice the way that this is drawn. You have a reagent 1, reagent 2, and then reagent 3. If you drew it out like this, drawing it out like this implies that first you do one reaction in like a round bottom flask. It's called a one-pot reaction. And then, since you have both of these reagents over the single arrow, numbered 1 and 2, that implies that all of this would be done in the same pot, and you don't have to isolate the intermediates. Okay? So you would just carry out the first reaction, and then you would simply add the second reaction, add the second reagent into the same pot and let it continue to react. If you draw a totally separate arrow, that implies that you must isolate this before you go on. Now notice you've drawn 1, or you have, rather, 1, 2, 3. So it's 1 parentheses, that tells you that's the first reaction, this is the second reaction, this is the third reaction, and since it's all over the same arrow, that tells you that you don't have to isolate the intermediates here. You can add the first reagent, let it stir to completion, then add the second reagent, let it stir and run to completion, then you add the third reagent, let it stir and run to completion, then you isolate the product. Okay, so that's the end of the first video, and in the second part we'll look at some more synthetic approaches.